The last video left off in the classification scheme for progressive waves with having already talked about longitudinal waves and transverse waves and just started to talk about orbital waves, which is where we're going to start right now. This is a pretty classic video of an orbital wave. I'll just let it go for a second. Orbital waves are ones in which the motion of the force generating the wave tends to be horizontal along the surface of the ocean typically. While the motion of the wave itself is circular, as you can see with this red ball, the wave is going by and frequently kids think that the water is moving, but instead it's actually just moving up and down. We're going to talk more about that as we go. So orbital waves, ocean waves, free surface waves, whatever you want to call them, what we're talking about are the waves you see on the surface of the ocean. Now, hopefully a good chunk of this is review, especially like the anatomy of waves, where we have the crest, which is the wave, the part of the wave that's above the still water level, the trough, which is the area below the still water level, wave height, which is a distance from crest to trough, which is usually given as a capital H, wavelength. In oceanography, we usually use L for wavelength. I know in physics they mostly use lambda, which is like right here. Some of the other oceanography books, you'll still see that. We don't really need to worry about that much. Other things you need to know, I guess since we've used it twice already, is still water level. That's a zero energy level halfway between crest and trough. So for example, in this picture, we can see the still water level. I'm not super crazy about this picture. So they're trying to show you a cross section of a wave, but also let you know that it's 3D. So there aren't two waves here. There isn't like one wave here and one wave here. A lot of kids think that. That's not the case. What we actually have is a single wave, and then it's going backwards into the page a little bit. So keep that in mind while you're looking at them. So what I want you to do is notice all the structures we just talked about here. We have crest, trough is right here. We have the wavelength being defined as any point on a wave and the exact same point on the next wave. And then the still water level is the area, the height of the water if there were no waves going by. So keep that in mind. There's one other thing I want to show you that I'm not sure you've heard of. It's called the free surface elevation. So when we're talking about wave height, which is really just the distance from the crest to the trough as seen here, that's like in one dimension, right? It's just vertical. Whereas free surface elevation is if you take into account one wave, basically from here to here, how high and how down low is the overall shape of the wave, and it assigns a numerical thing to that. We're going to talk about that because we do a little bit of math with free surface area. But whereas typical wave height, which is either just up or I suppose you can measure it from the crest down, looks at just one dimension. Free surface area takes into the raised or lowerness above or below seawater level of the whole wave. So it's sort of more like a parabola. There's some of it below and some of it above, and it assigns a numerical value to that. Here's a wave diagram that came with the wave flume. I actually like this one a little better. It's a pretty typical idealized wave. That's an had a little burble there. This is an idealized wave. That's an important idea because are waves ever really this perfect in nature? Not so much. So it's sinusoidal in shape, right? We have a sine curve. Sinusoidal. We're going to talk about why this is a deep water wave when we get to deep water waves. It has relatively small amplitude. That becomes important when we get to really large waves. Things begin to change about their shape. I don't know if you can picture the wave tank in your mind, but we tend to get this other shape, which is not sinusoidal. It's tricoidal in shape. I can't type. Coidal in shape, and that's those pointed ones. We'll talk about that again as we go on. And this formula, which has a lot going on here, where N is free surface area, A, or sometimes it's given as the little fishy, is amplitude. X is the distance, is the distance from the disturbing force, the origin. T is time since the wave left the origin. K is radial wave number. It's also sometimes just called wave number. It's given by the formula 2 pi divided by wavelength. This almost ends up acting as a constant, so you don't really have to worry about that too much. And where our little sigma is angular frequency, 2 pi divided by, and in this case, T is period, not time. So there are a couple things. Let me highlight the key math things here. keep in mind that, I kind of erased it. T is given, little t is time, big T is period. That's going to get important later on. I know everybody loves physics, so we can talk about how these things are valued. But we also have little h and big H. We're going to talk about those as we go too, so make sure you write them down carefully in your notes. But this wave diagram includes one of the ideas we're going to talk about in the next slide, which is wave steepness. A lot of kids think that wave steepness is just the angle from the crest to the trough. You got to remember, wave steepness is for wavelength. So what we're saying is wavelength, say, I don't know, from this peak to this peak, it's the height, the distance from crest to trough, and the wavelength, which runs this whole length. So that's why we end up with sort of this line as opposed to this line. So that's the difference between wave height and wave steepness. If we are learning all these formulas, we're obviously going to be using them down pretty soon. Oh, let's go one more slide forward. So more definitions: wavelength, distance from one point on wave to the same point on the next wave. Here's a super fun formula for how wavelength is actually calculated on a wave. I put this here. We're going to use it in class only insofar as to explain other formulas. Hopefully you know what most of these things are, but we can go over them real quick. L is wavelength. Again, this is one of those things that can be different in oceanography versus physics. Wavelength in oceanography is always given as L, or usually given as L versus lambda. G is the gravitational constant. Since it's a science class, we would use 9.81 meters per second squared. T is again wave period, the time for one wavelength to pass a fixed point, squared, divided by 2 pi. I'm assuming you know pi. Tangent, and this is the little h. Little h is not wave height. So little h is water depth. That's the distance from the still water line down. And that would be multiplied by 2 pi, depth again, divided by length. I think you might notice that there are a lot of variables that occur on both sides of the equation. That is because waves are complicated, and the math is too. So I will just say outright, I don't expect you to use this formula, and I don't expect you to memorize it, but I hope that you would be able to explain what each variable stands for, especially since I just explained it. Wave height, again, next one is height divided by length. Wave steepness is really important because the wave steepness explains when a wave, quote unquote, breaks. So if the ratio of the height to the length is greater than 1/7, then what happens is the wave begins to topple over. It reaches what's called critical steepness, and it begins to break. So what this can do is it allow you can make predictions. For example, if wavelength, and this time it was given as lambda, is 7 meters, at what height is the maximum wave, the height the wave can reach before it breaks? And hopefully some simple math, you would see that it would reach no more than 1 meter. Wave period we already defined. Wave frequency, it is only used very rarely in oceanography. We tend to use wave period for almost everything else, but it's the inverse of period, so it's 1/t. So I was going to walk you through one of those problems where there's the formula for free surface area, n is equal to, the alpha sign, blah, blah, blah. But I think we're actually going to do that in class. So what I want you to do is write down these numbers, and on Friday we'll go over them. So when we're talking about orbital waves, so far we've sort of just been doing anatomy of waves, but there's other characteristics you have to know because, of course, there's always more. This diagram is also in the book. I like this one a little better. So there's an important idea that I don't know if you covered in physics is called wave base. Wave base, funny enough, doesn't seem to have a symbol, but wave base is defined as, so let's look at this diagram for a second. We have wavelength here. If you take the wavelength and rotate it this way, and you were to draw it down this way, I made it a little too short. The 1/2 the wavelength is what's called wave base. It's not just an arbitrary definition. Wave base is the point at which, so we have all these orbitals, and as the wave moves, the particles move in this direction like we imagined. You notice that the particles are moving in smaller circles. That's because they're rubbing against each other, and that creates friction. When you have friction, your energy, some of the energy is lost to the environment. So there's less and less energy with which the particles are moving. The point at which there is no energy or negligible water movement is called wave base. So if you were to measure or put something in a particular buoyancy, it would move in a circle here. But if you kept going down, there'd be no movement. You can see this in our wave flume where sometimes when we have very gentle waves moving by, you can see the pellets move back and forth slightly. But when we have really big waves move by, they move by a lot. That's because they're whether or not they're above or below the wave base. So this is something we're also going to be working with. Next slide. And more to take home, hopefully, the idea that there's this waves move, the particles that make up the wave move in a circular pattern. So this is a rubber ducky. I think it's supposed to be a rubber ducky. It does have weirdly realistic feet. On the other hand, ducks aren't typically yellow. So we have a wave going by, and there's a little rubber ducky. The wave is moving to the right of the screen. And we have the duck. So what happens is the wave begins to move by. The duck moves up, keeps going, comes back down, and so on and so forth. This is the idea that there is little to no forward movement in a wave, even though the wave is going that way itself. This becomes important because there is a very slight movement. Here's our duck's original position, and here's our duck's final position. The difference as one wave goes by between the duck's original position and its final is called wave drift. Wave drift is physics-wise a really interesting problem, and you see it much more obviously when you get closer and closer to shore. But wave drift, oh, there goes my cat. So you need to know what wave drift is. We see this in the flume when we put the orange ping pong balls in. They will move slightly forward, especially the bigger the waves. One of the other things I want you to take away from this is, okay, so here we have wave height. Oh, and I should probably point out, do you remember what this wave shape is? It's not sinusoidal anymore, correct? It's a tricoidal, pointed crest, rounded trough. So as this duck is moving, it makes an orbital. The diameter of the orbital in any direction, drew something there, is going to be exactly the same as wave height at the surface. So the diameter of a wave as it's moving at the surface is going to be equal to wave height. That becomes important mathematically when we do some other problems. Wave speed. Wave speed is usually called celerity and not speed. So when we do that, it's typically given as C instead of S. I believe your book does use S in some formulas. For the purposes of this class, we're going to use them interchangeably, and I, from habit, typically use C. So here's the formula. Look, isn't this the best formula ever? It's so simple for now. So let's go over what they mean. Hopefully this one's really easy. C, wave speed or celerity, is equal to L, big L being wavelength, over T. Please, children, remember that T is not time. T is period. So this formula for wave speed works for all waves. If you know the length and you know the period, you can figure out speed. And it is the most accurate formula. There's no estimations. There's no constants. It's a perfect relationship. So what you should take away from this, and I do know this is here, but we almost never use it. What I want you to take away from this is if celerity is given, if you're asked to find celerity and you're given length and you're given period, calculate speed that way. You're like, well, don't we have to know those? And the short answer is no. This is because, let's talk about the other types of waves we have. There's other formulas. So we have to define something before we can talk about the other math. What's a deep water wave? A deep water wave is different than a shallow water wave and eventually transitional waves, in which it is defined as a wave in which the water depth is greater than 1/2 the wave base. The water depth is greater than 1/2 the wavelength. What this means is it's a wave that's going by in water that's deeper than where those orbitals start moving. So those orbitals are moving freely. They're not interacting with the bottom. These are deep water waves, classic ocean waves where the energy doesn't reach the ocean floor. There's a formula for this right here. L is equal to gt squared over 2 pi. That, again, where g is gravity, t is period, and for the love of God, I hope you know what pi is. What this means is that the dominant factor when we're talking about the speed of a deep water wave is the wavelength. And the general relationship is that the longer the wavelength, the faster the wave is going to move. Waves with very long wavelengths tend to travel very, very fast, and conversely, smaller wavelengths travel less fast. We can play with this with the waveform and see how that works, but it's all the time. So keep in mind, deep water waves, the key thing here is that the water depth is greater than the wave base, or 1/2 wavelength. This is a graph from your book that shows the relationship between wavelength and speed, and while we can see there is a relationship as wavelength increases, so does speed. This is not a perfect linear relationship. It's more exponential or logarithmic, actually. And we'll talk about why when we do some formulas. But what I do, and I should have emphasized this on the last one, make sure you add this formula to your notes. This one we will be working with. And this will tell you the wavelength of a wave, but only for deep water waves. So unlike the celerity formula, which works for all waves, this formula right here, which I just scribbled all over, only tells you this length of a deep water wave. We did this one already. Shallow water waves. So unlike, oh, there's a typo here. Uh-oh. All right, let's fix this right now. We're going to scribble that out. In a shallow water wave, wave depth, little h, is going to be less than, and this is vital, 1/20th, not 1/2, 1/20th of wavelength. This, if you notice in this diagram, we still have a tricoidal waveform, which is actually not particularly accurate. Let me just erase that. Okay. But the orbitals should look different to you. This is because the orbitals become smushed. I guess that's not a technical term. But what's happening here is this is ocean floor. Anytime you see a diagram of shallow water wave, or hint, hint, make a diagram of a shallow water wave, you need to include the ocean floor, which is right there. Because you need to show that the ocean floor, remember, this is our wavelength, correct? And while this is not terribly to scale, if we rotate it this way in a shallow water wave, the ocean floor should be at 1/20th of wavelength or less. Meaning, let me see if I can erase this. Yay, that's fun. Meaning that the orbitals that go all the way down to wave base are now no longer just interacting with water. The ones at the bottom, the orbitals all the way down here, as they hit here, there's friction, and a lot of it. And what this causes is for the bottom part of the orbitals to slow down. They slow down and slow down and slow down, which in turn slows down the ones above them. And you end up with not only smushed orbitals, but a wave that's slowing down. So what we say is that the orbitals are feeling the ocean floor. I think perhaps interacting is a better term. And this causes friction, and our orbitals change shape. We have another formula. So the formula here is that length is equal to period times the square root, g being gravity, and h is depth. Shallow water waves are completely, the speed of them is completely controlled by the depth. We're going to talk about that more in class and do some math to prove that. But as I said before, deep water waves, the speed is completely proportional to the wavelength. That is not true with shallow water waves. The speed of a shallow water wave is a function of its depth. The shallower the depth, the more friction there's going to be with the bottom, and the less speed the wave's going to be able to travel forward with. Shallow water waves include wind-driven waves, and here's a caveat, only when they reach shore, so breakers. The waves you see breaking on the beach are going to behave as shallow water waves. When they're way out in the middle of the open ocean, those are deep water waves. Then there's tsunami. So tsunami and any really, really big waves with really, really long wavelengths. These are shallow water waves. And this is weird to think about because you probably know they move across the open ocean. The ocean is on average only 4 kilometers in depth, and the wavelength of these are substantially longer, like hundreds of kilometers. So what happens is, even though the ocean is deep, it's not deep enough to be more than a shallow water wave in relation to tsunamis. Tides even more so. I think we mentioned very briefly in the other video that the tide is really just two waves that are depending on perspective, rotating around the Earth, or the Earth is rotating under them. What this really means is that the wavelength of a tidal wave, a true tidal wave, not a tsunami, is literally 1/2 the circumference of the Earth. So the depth of the ocean is not remotely close to that, so it is, of course, a shallow water wave. Transitional waves, super fun. Transitional waves are, oh, look, another typo. Oh no, no typo. Have characteristics of both deep water and shallow water wave. Fun fact, I won't make you calculate any formulas for them, so finding transitional waves are probably your favorite. But you do need to know mathematically at what point they occur. A shallow water wave occurs when depth is less than 1/20th the wavelength. A deep water wave occurs when depth is greater than 1/2 the wavelength, and a transitional wave is in that sweet spot where the depth is between 1/20th wavelength and 1/2 the wavelength. So I guess that begs the question, if it's exactly 1/20th wavelength or exactly 1/2 wavelength, is that a wave that's in transitional or shallow water? Based on the very limited, I only found one source that even makes a call on that. They had, if it's exactly 1/20th, if the depth is exactly 1/20th the wavelength, or it's exactly 1/2 the wavelength, we're going to call those transitional. To be perfectly honest, I probably won't ask you that on a test or a quiz because that's a little mean. This is just a diagram showing the same thing. You can see here that the orbitals are slightly more elliptical than perfectly round. They're interacting just slightly with the bottom, and that's all you really need to take away from this. Oh, goody. We've reached the end of this slide. So I will see you guys next class.